So let's get a review of some function basics. So a function relates two variables together, typically x and y, where x is the input, y is the output. If you needed to find the domain of a function, that would be all possible inputs, so all possible x values, range, all possible outputs, so all possible y values. So for our notation, we have y equals f of x, which means if we have this output y, it's coming from this input x into this function, which is called f. So f is just the name of the function. Average rate of change is something that we calculate quite a bit, especially going into calculus. This will become a big part of your work, where you look at the difference between two output values over the difference in the inputs. And then one you'll see quite a bit of in calculus that we try to bring into our pre-calculus 1 class is the average rate of change from x to x plus h. So it's like having an input and then adding something to that input. And it's the same structure. You take the difference in the outputs over the difference in the inputs, and that denominator just simplifies to just h. Sorry, there's a little typo there. That should be x, not h. So x plus h minus x, and that will leave you with h. So this is just a special form of the average rate of change called the difference quotient, which you'll see pop up at the beginning of calculus. Okay, so reading function notation from a graph, it's coming from coordinates and the fact that each coordinate gives us input and output values. So finding m of 1, so that's telling us that x is equal to 1. So what we do is just go to x equals 1 and then look up the corresponding coordinate on the graph. So we have this coordinate that's x equals 1, y equals negative 1. So if we're solving for that function notation, m of 1, the output is negative 1. So we're just plugging in the y value. Same thing for m of 3, we're going to x equals 3, so 1, 2, 3. And notice that we have kind of two locations here, but an open circle means it's not defined, so we don't want to use that one. Instead, we want to use a solid circle, which is the 3, positive 1. And so if we want to evaluate m of 3, we're plugging in the output, so the y value, which is the positive 1. Alright, m of 7 minus m of 5. So we want the input for when x is 7. So if we go, let's see, 3, 4, 5, 6, 7. So we have this coordinate 7, 2. So that means our output to evaluate m of 7 is equal to 2. And then we'll have minus m of 5. Let's see, that's 7. Here's at 5. So we have 5, negative 2. So for m of 5, we want to plug in that output of negative 2, and I'm going to use parentheses here because of those negatives. So m of 7 minus m of 5 all over 2, and this right here is our average rate of change, like where that 2 came from was from 7 minus 5. So we're looking at the average rate of change between x equals 7 and x equals 5. Let's see, in the numerator, 2 plus 2 is 4, divided by 2, so overall, this is 2. Now visually, what this average rate of change is doing is it's finding the slope between 2 points. So it's that if I drew a straight line from 7, 2 to 5, 2, so if it didn't have any curvature to it, that straight line has a slope of 2, and that's exactly what we calculated there. It's that if you draw a straight line between those 2 points, your slope is equal to that average rate of change. All right, m of x equals 2. Now what we're being given here is the y value. So with these, we think kind of horizontally. So what I would do is think of at y equals 2, I would visualize this horizontal line. And what I want to do is include every point where we intersect with that y equals 2. So like here we have this coordinate, let's call that about negative 1/2 with a y of 2. Again, that open circle is undefined, so we would not use that. But then we also have that coordinate 7, 2. So we have two possibilities for x here. X can be negative 0.5, or x can be equal to positive 7, since we have two intersection points. And in this format, we're trying to figure out what goes inside the parentheses. For -3, so if I go to -3 here and visualize this horizontal line and looking for all intersections, I do not have any intersections, which means that would be no solution. All right. So that's working with function notation graphically. Now algebraically, we're going to work with this function here, x squared over x squared minus 2. We want to simplify the following. So f of -8 means we're plugging in -8 for x, and what I like to do with these is set up parentheses where x was, and then we're going to plug in our input. So this will give us 64 over 64 minus 2, which is 64 over 62, and just reducing that down, that should be a 32 over 31. That'll be done. Same thing for f of 2. Again, I like to set up my parentheses. It's especially important to use the parentheses with the negative numbers because that negative is squared, so you should be getting a positive out. It's a very common mistake that's made in calculus. Like the calculus isn't too bad, but just remembering to square your negatives, that's where things can kind of fall apart. Alright, this is 4 over 4 minus 2, so 4 over 2, which is just equal to 2. Alright, here we have input, but it's a function, but it's still the same idea. We have something squared over something squared minus 2. It's just what we're plugging in is this 3 over x, which equals 9 over x squared over 9 over x squared minus 2. Now, this is a complex number because we have fractions within a fraction. So what we want to do is clear out those denominators. So you want to multiply everything by the least common denominator, which in this case our least common denominator is x squared. So what I want to do is multiply the numerator by x squared and multiply the denominator by x squared. Now in the numerator when we do this, those x squareds will cancel out. So all we'll have left over in the numerator is 9. And then over, and down here we're going to need to distribute the x squared. So when we have 9 over x squared times x squared, they'll cancel out. So at the beginning there we'll just have 9, and then minus 2 times x squared, which is 2x squared, and now it's no longer complex. We don't have any denominators within our fraction there. And then I would just look to see if I can factor anything or reduce anything down, but this is going to be stuck just like this. You might be tempted to cancel out those 9s, but we absolutely cannot because of that subtraction right there. That subtraction is grouping that denominator together, so the only way we could cancel that is either by somehow factoring it, which we can't, or seeing that entire piece in the numerator. Like if that was 9 minus 2x squared, then we could cancel things, but you'd have to see the whole piece with the subtraction too. Alright, so there's some function review of plugging in and evaluating our functions.